CRO is basically a device like a digital display. CRO should be considered CRO should be considered as a monitor. Actually, it was the first monitor they made. And now, obviously, monitors are a lot. We have gone through much far away. But CRO is still a very powerful display device. It is capable of showing the data. It is capable of showing data in a graph format. This is a graph which is showing the life status, and there is a fluctuation which doctors use. First, you, after giving the heading, copy the introduction.
Okay.
Working, give a side heading working and mention working not in course. Last year, I had explained that whenever syllabus changes so much and there are many updates, so there are many updates. So you have to remember that you should know what topics are there, what topics have been removed. Obviously, they are present. They are present in our past paper, obviously.
Yeah.
Now, give us side heading applications.
Okay.
There are some important applications. They are following a rule that CRO is a very accurate device. It can register very small values. CRO is famous for its digital nature. What's a digital nature? A digital nature is the extreme level of sensitivity. When you draw, when you look at this screen and you remember that any movie scene or any, may God not, any reality, you see someone on a someone is there admitted in a hospital and doctors are taking reading from this machine, you will notice that this apparatus is extraordinary sensitive. A minor change will be there and it will register it. So CRO is known for its accuracy for small values. Actually, accuracy matters when it's a small number. When you are taking the weight of, suppose, grocery like vegetable, then small numbers do not matter much. But when you're taking the blood pressure of a patient, then a small fluctuation matters a lot. This is where the CRO type device comes in. So you have to copy now this screen.
Yeah.
The important applications, you have to copy this list.
Yeah.
Now, look at this list as a display device. This is what we have already discussed. It is being a graphical display. It shows the data on a graph. It shows the change as a waveform. It's a timing device. It is, in our course, it is the most accurate clock, stop clock, you can say. Voltmeter is always there. Voltmeter, you know very well, it's used to measure PD. So this machine can measure the PD to a very high degree of accuracy. Now give us side heading, readings and calculation. Readings and calculation are actually now in the course. This is leftover. This topic is not in terms of any working now. It's only like a graph reading. This apparatus actually, this apparatus is actually it actually like a graph paper. It's a digital graph paper. So when you take out a graph paper, new graph paper, you mark numbers on it. So suppose this is a graph paper. This is a graph paper. So you can write 0 here, 1, 2, 3, 4, -1, -2, -3, 1, 2, 3, -1, -2, -3. It is just like this. Now, this thing which I have done has to be controlled digitally here. So there are multiple controls here which are used to calibrate this device. So whenever CRO is used, it has to be calibrated. It is actually a device which works on the principle of graphical calibration. What's a graphical calibration? It actually means simply that whenever you are dealing with a CRO, it's like a digital machine and you need to input data in it. Now, this is a CRO screen, okay? You can see there is a screen here and I'm changing the pattern. Look, this is the screen pattern and 300 frequency is the input. This is the frequency input. Now I change the setting of the machine. Look, the display. Keep on looking, I'm decreasing the number on the scale and the graph is getting big. Look, now the shaded part, if you look at here, the shaded part is time period. We used to do this calculation in our O-level physics. The time period is the time for one complete cycle. It is the time period for one complete cycle. So this is how we calibrate it. We move the knob like this. Now it is not readable. It is still difficult to read, but now it is better to read it. This is more easier to read it. Now, what is peak voltage? Peak voltage is the output voltage. I will put the signal, suppose at 4.8. Look at the screen. Again, as you decrease the scale, it's a rule of graph. When you decrease the scale, when you take smaller number on the scale, graph becomes big. It's not readable. So we move it back and now it is better. You can read it easily. This is basically peak voltage. Peak voltage is the voltage. Peak voltage is the maximum voltage of a display. So CRO has two major contributions. It can measure the time period. And once you measure time period, you can definitely measure frequency also. Second, it can measure voltage. CRO is also capable of showing different types of voltages. Now you can see here, this is a, let me switch on the scale. This is my voltmeter, voltage axis. Look, this is the voltage axis. Now I move the The display is quite quick, quite short, quite compressed. Now it's looking better. This is how you actually calibrate your graph also. Now I have scaled it. Now this is called sine theta curve. Look at this one. It is called rectangular curve. And this is called triangular. So there are three famous types of output signals: sine curve, square curve, and triangle curves. After giving this heading, write under it that the output of a CRO the output of a CRO is a graph of voltage against time.
Done.
So this is, you copied it, right?
Yes.
You have to copy this screen.
Done.
The common readings are time period, frequency, and peak voltage. Frequency is known to have a formula, number of cycles in time in second. Time period has a formula, 1 upon f, and peak voltage is actually the amplitude. These all were in our O-level physics, but obviously it has to be recollected here. It is surely under the title of CRO, but is actually a graph reading. You have to copy this screen now.
Done.
Now, this is a graph memory callback. Y-axis is amplitude, which is the peak voltage. You can see x-axis, the time for one cycle. The time for one cycle is time period, and 1 second is 10 power 3 millisecond. This is a quick recall, and I hope if you copy it, you can recall it back. This was in our O level, and the name of the chapter was Waves.
Done.
Now, the example is here for our discussion. No need to copy and just watch it on the screen. And the scale is given for, suppose we see for x-axis. For x-axis, the scale is 2 millisecond per division. So if I'm working for time period, I will mark the time for one cycle. This is one cycle. Then I count the boxes. Then I count the boxes. So when I count the boxes, I will get 4 boxes, and this is the scale. So what I will do, 4 into 2, 8 millisecond. This is the time period. So it's very simple. It's a game of counting boxes. You have to count the boxes, and once you get the time period, then frequency is equal to 1 upon time period, 1 upon 8 into 10 power minus 3. Similarly, when you talk about the peak voltage, this is the peak voltage, and you say it's V naught, you will count the boxes. There are 2 boxes. This is the scale. So you will take it here, you will say 5 into 2 is equal to 10 millisecond. So it means, sorry, 10 millivolt. What is the concept actually to be learned here? That it's a game of counting the boxes. Count the boxes and multiply it. Count the boxes and multiply it with the number of units. So now right under it, a side heading method. Count the divisions. Count the divisions and multiply with the scale. Then give a side heading calibration So a CRO has to be calibrated before every experiment.
Done.
This is the output. You have to copy this screen.
Done.
This is the actual output of a CRO, and you can look at the screen and you can find many scales, but two main knobs are there. And this is the 5 volt, this is the 2 millisecond. So when you start reading, you will see that one cycle is not coming in whole number of cells. Second cycle is finishing here. First cycle is finishing here, but not in whole boxes. But third cycle is finishing in whole boxes. So you will go on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 boxes. Now there are 10 divisions for 3 cycles and one is 2 millisecond. So you will say 10 into 2, 20 millisecond for 3 cycles. So when you know the time of 3 cycles, you can definitely convert it into time for 1 cycle. Similarly, once you count the vertical boxes, you can get the V naught, but you have to be careful that this time there are some very small numbers. There are some small divisions also. Now, give a heading, digital and analog.
Done.
This is the digital version. It has a display. This is an analog version. It has a scale. Digital instruments have a display. Analog instrument has a scale. You have to copy this.
Done.
Look at this screen. This is an analog vernier caliper. This is a digital version. It has a display. So right under it that digital display, digital meters are more accurate. Digital meters
Done.
digital meters are more accurate because they can show more number of significant figures
Done.
Next line, right under it, change the line and write under it that analog instruments are less accurate but more reliable. Analog instruments are less accurate because you cannot read many significant figures from here. This is a limit here. You can read 1, then 1.1, maybe 1.2. But here, decimal can go till the screen is there. So now, give the heading, types of errors. This is an important topic.
Done.
What is an error? Actually, error is the difference, and error is a deviation from accuracy or correctness. You have to get an answer, but your answer deviates from the true value. This is what we call as an error. You have to copy this screen.
Done.
In our course, there are two errors. One is called random and one is called systematic. I hope you just look at these names and you will get it back. We are making this chapter in full because we didn't make proper notes on that. So that's why these all topics, important, less important, are here. Now you have to copy this.
Done.
Now, what was a random error? The word random itself has a complete concept. Whenever you use the word random, random means no particular direction, no particular value. Random can be anything. So, in our conceptual sense, when you say silly mistakes are random, when you say formula error, random, you had to square it, but you made a cube. This is a random error. So random error has no physical range. It can be any number. It can be too high, it can be too low. Then what is systematic? The word systematic itself has a meaning that it is an organized. You know that you will be 10 minutes late. It's a systematic error. You know that there is a zero error in your machine. You know that your stopwatch is 2 seconds ahead. You know that your watch is 5 minutes ahead. This is called a systematic error. Now, first number is random error. And then the definition has to be copied.
Done.
A random error is not fixed. It actually fluctuates in magnitude and in direction. You have to copy this.
Done.
Now, it means that it is not a fixed error. It is fluctuating in number and also in direction. Now, this is the way. Graphically, it appears like the scatter. Graphically, it appears like a scatter on the line. The points are scattered. This is the best fit line. So the scatterness shows the randomness. The scatterness shows randomness. You have to now copy this screen.
So for line of best fit, do we make it in such a way that there are equal points on either side, or can we make a
Yes.
line which connects most of the
No, no,
points?
the first point is right. It should be dividing the population from the possible symmetry, but it is not necessary that it passes for many points. So maybe it passes only 2 points. That's no problem. You have to copy this.
Yeah.
So we keep it up to here, and we will inshallah continue in the next class. I have also sent you a class possible if you can take for paper 2, paper 4 actually. So you should try to remain in touch. If possible, take that class also.
Okay.